Okay, hello everyone. I've decided that I'm going to do a set of videos on cube combinatorics, or calculating how many positions you could have for a given alg set, put bluntly. This was inspired because I've noticed that quite a few cubers don't seem to know how to do this, which is perfectly reasonable to be honest, as proper combinatorics isn't taught until quite a bit later. So, this episode will be on permutation of the pieces. So, as you all know, every piece on a 3x3 Rubik's Cube is unique. And one additional thing is corners can only go in corner positions, and edges can only go in edge positions. And I'm sure all of you know this. Now, say I have 8 pieces that I want to find the positions of. Orientation doesn't matter for now, so let's just say I have all of these 8 pieces oriented, all the 8 corners oriented, and I want to find how many different positions they can be in. Now, I'm going to represent each of these pieces with a unique card. So there are 8 pieces, and 8 different cards, and 8 different slots. Now, first let's simplify the problem. Say I had just one piece, and one card that can go in there. Clearly this card can only go in one slot, so we have one position. Pretty obvious so far. Now, if we move to 2 pieces, well then we'd have, and 2 different cards, then we'd have a choice now. This first card can go in either of these 2 positions. It could go here, or it could go here. So, if we go put it there, this card will only have one possibility, this position. Alternatively, if we put this card here, this will still only have one possibility, but clearly these 2 positions, this position and this position, are not the same. So, we have 2 different positions if we want to put 2 cards in 2 slots. Let's go one step further. Say we have 3 cards this time. We have one card here, and it can go in any of these 3 positions. It could go here, it could go here, or it could go here. This first card, if I put it here, say, this second card can go in any of these 2 positions. So it could go here, or it could go here. If I put it here, for now, let's say, this card will have one position it can go in. Here. So that will give us one unique position. Now, if we weren't being very efficient about this, we could just say, right, let's put this card here. Oh look, we can have another 2 positions for those 2 cards. Then we'll start again. What if we put this card here, and we can have another 2? And then we'll put one more card here, and have 2 more. Now clearly, that would not be a very quick way to do it, especially when we go on to really, really big numbers of cards. Here it wasn't so bad because we only have 6 positions. But imagine we had 4 cards, or 5 cards, or even 8 cards, or 100 cards. This will not be a very quick way. So what we could do is we say, well, I have one card. It can go in any one of 3 positions. And once it's in those 3 positions, my next card can go in any one of 2 positions. So so far we've got 3 positions times 2 positions. And the last one, it doesn't have a choice, it's only got one, wherever the other two don't go. So that means we'll have 3 positions times 2 positions times 1 position. Or we'll have 3 times 2 times 1, or 6 different positions. Now, as you saw before, when we were counting, we got 3 2s. Or we got 6 different positions. So, let's go back to our original problem. Imagine we have 8 different cards. Our first card can go in any one of these different 8 positions. So we have 8 positions. Our next card can go in any one of the 7 remaining positions. So we have 8 positions times 7 positions. Our next card has any one of these 6. So we have 8 positions times 7 positions times 6 positions. And if we continue, we have 8 times 7 times 6 times 5, 8 times 7 times 6 times 5 times 4, 8 times 7 times 6 times 4, 5 times 4 times 3, 8 times 7 times 6 times 5 times 4 times 3 times 2, 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So, the general method we can use is we find how many different positions we have and how many different cards we want to place. And we use that multiplied by all the numbers below itself. So if we had 6 cards, we'd want 6 times 5 times 4 times 3 times 2 times 1. If we had 2 cards again, we'd have 2 times 1. Now this will function, function I'll call it, is called the factorial function. It's denoted as 8 with an exclamation mark. And this just means take this number, multiply it by all the numbers below itself. So, say we wanted to calculate the number of positions for permuting just the 4 corners on a 3x3. We have 4 corners and 4 pieces. So what could we do? Well, we take our 4 cards and we show that there are 4 different spaces. So, first corner, there we go. Second corner, there we go, 4 times 3. Third corner, 4 times 3 times 2. Last corner, 4 times 3 times 2 times 1. So, we get shown that there are 24, 4 times 3 times 2 times 1, unique different positions which the corners can be in. Now, I can already tell some of you are going to be saying, but Shadow Slice, some of these pieces, there aren't 24 different EPLL cases. There are only 3. The opposite swap, the adjacent swap, and the no swap. Well, solved, I guess. Now, this is where the Rubik's Cube is slightly different to just a deck of cards. So, here we can rotate the top layer. So what we've done here is we've counted, well, what if these 2 are swapped? 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 What if these 3 are swapped? And so on. So what we'll need to do is we'll need to divide by 4 different rotations. Because we'll have 24, but we can reduce them by 4 because of how many times you can rotate. So we'll have 24 divided by 4, which is 6 different pieces. If we have 6 different positions, well, that's still not quite right. Because one other thing we have to take into account here is the symmetries of these pieces. Our solve state, well, that's all been taken care of by rotations. Our opposite state, similarly, also has just been taken care of by rotations. However, our adjacent, we still have this adjacent swap, this adjacent swap, this adjacent swap, and this adjacent swap. So, what we can do is we just take that case and say, well, there's another 4 lines of symmetry which we can get rid of here, which will leave us with the 3 cases. Now is probably a good time to explain that most of these techniques that I'm teaching you on a Rubik's Cube will not always give you the accurate number. Quite often they will slightly overestimate by probably somewhere in the range of 50%, though that can be down to 0% in some cases. So, we could use these techniques to give a rough estimate. So, let's try something different. Let's say we have, as we do in a few alg sets, we have, say, 6 pieces, and we only care about the permutation of 2 of them. So say in LSE, well, the second step of LSE, yes, we have 6 different pieces we want to permute, but we only care about 2 of them. So, we have 6 different slots and 2 different pieces. How many cases could we get? I'll leave it for a second, let you think about how we might go about calculating this. Okay. 2 different pieces, 6 different slots. Clearly our first piece can go in any one of these 6 different slots. It really doesn't matter. But continuing as we did before, let's just say we put it here. That means our second piece can go in any one of these 5 remaining positions. Or perhaps here. So we have 6 positions times 5 positions. Or 30 different possibilities of where those pieces could be. But what's a quick way to calculate this? Well, we could just say it's the same as number of different slots we have, or 6, factorial again, so 6 times 5 times 4 times 3 times 2 times 1, divided by the number of slots that we don't care about. So the number of slots we have divided by the number of slots we don't care about, which will give us 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1, or 6 times 5, as we expected. 30 different positions. So, one other interesting thing that we have on the Rubik's Cube, but not necessarily anywhere else, is that corners and edges cannot interact with each other. A corner can't go in an edge slot and an edge can't go in a corner slot. Parity, as it's perhaps unfortunately referred to. Now, sorry about that. Neighbour started doing the lawn. So, if we have... Now, a Rubik's Cube can only be swapped two swaps at a time. So here, if we do a J-perm, we have one corner and two corners that have been swapped and two edges that have been swapped. This is distinctly different to something that can happen on a 4x4 or parity, where you just have two pieces swapped. But on a 3x3, so another example, in a Y-perm, two corners swapped and two edges swapped. So this means if we're calculating a position with both corners and edges, let's say we want to calculate the number of last layer positions there could possibly be. We have four corners, the number of PLL positions there could possibly be. Four corners, four edges. So, we take our first four corners. We can already know there are 4 factorial positions. So 24 different positions to start with. And our second set. Now, these pieces, while the first 2 can go in any way they like, these last 2 must go in a specific position, depending on what these pieces are doing. So these pieces these pieces can only go in this position with these cards, but if we swap these 2 around, these 2 must go here. So essentially, what we can do to divide by 2 is what we do to eliminate parity is just divide by 2. Nothing more complicated than that. And by dividing by 2, well, it completely gets rid of our problems. So, for the last layer positions, we would have 4 factorial times 4 factorial divided by 2 because of the parity. And then remember all of the AUFs, we divide by 4 again. So we end up with 4 factorial times 4 factorial divided by 2 divided by 4. And that will give us 72 different PLL positions. As I said, this is not entirely accurate because some cases, such as the T-perm, have a line of symmetry down them, just like we were talking about with the adjacent swaps. So that will mean that some cases will be duplicated still in our count, but it will give you a very good estimate of how many different permutations you could have. So that's it for today. Post any questions you might have down in the comments, and the next episode I will be doing will be one on orientation. And afterwards I think I might do one on how you can calculate orientation and permutation both together to find a full alg set such as ZBLL or the number of last layer positions. And we'll just see what happens after I finish filming that episode. So, post any comments or queries or suggestions or improvements or anything like that down in the comments. And I hope you learned something from this video, and if not enjoyed it, and I will see you all next time.